Okay, so introducing coordinate planes. Whenever we're doing graphs in this course, we need to make sure that we have at least three things labeled. We need to have the x-axis, which is the horizontal. Okay, so when we're looking at this, the x-axis is going to be our horizontal. Okay, so that's our horizontal axis. It's the line that goes right through the middle of the graph. Our y-axis is our vertical. And we need some sort of scale. So you can look, you can see I've got an x, I've got a y, I've labeled my axis. Okay, even if your scale is something like this, if you count out 5 squares, so 1, 2, 3, 4, 5, and I put a 5 here, 1, 2, 3, 4, 5, a 5 up here, 1, 2, 3, 4, 5, -5, and -5. That would be good enough, like that would be the bare minimum. Typically what you're going to want to have is something like, if we were to do, so we've still got our x and y, and then we would do something like 2, 4, 6, 8, -2, -4, -6, -8, and the same thing on the y values. Okay, you don't have to do every box, but you do need to label some sort of scale, otherwise it's not right. Okay, looking at this graph again, if we were talking about coordinates, we're talking about points on the graph. But when we talk about quadrants, there's actually 4 quadrants that we've made up. So there's a T from the axes. Quadrant 1 is the most common quadrant. Okay, it's the top right. It's got a positive x and a positive y. Quadrant 2 is actually here. So quadrant 2. It has a positive y but a negative x. Quadrant 3 is down here. It has a negative of both. And quadrant 4 is our last one. It has a positive x and a negative y. Okay, so if you hear the word quadrant, that's what we're talking about. You don't have to label them, but you should know that. Okay, points on a Cartesian plane are also labeled as ordered pairs. They're called ordered pairs because it's always an x and then y. Okay, so if I were to look at the points that are on this graph, A, we're always going to label them with 2 numbers and that. So it always, without even actually looking at these points, I know that it's going to look like this, and I'm going to put some numbers in. A, I always do my x's first. A is 1, 2, so -2, and then it's up 1, 2, 3, 4, 5, 6, 7, so -2, 7. Always x and then y. B comes down from -7, and it goes down 2, so -2. C went over 2, down 7, and I'm kind of trying to write in a different way of looking at each of these. Oh, it's +2, sorry. I'm trying to look at a different way of going to each of these points each time, but you're doing the same thing. And then finally D, we've gone over 7, we've gone up 2, so this is 7, 2. Now it says, label the following points or plot the following points on the graph. So now we need to put some more points on. So E, we're doing 3, 4. We always start horizontally. Okay, so we're going to go in 3, 1, 2, 3 to the positive, and then up 4. So my point, I'm going to make my points a little bit bigger here. Let's do that. My point is 3, 4 is going to be right there. Okay, and that's E. Okay, when we're looking at F, we have -4, so I'm going to -4, and then I'm going down 7. So -4 to -7 is going to be right there. So that's F. Now, G is 0, 9. 0 means I don't move left or right. All I'm doing is going up to +9. It's nice and easy when there's a good scale. Okay, the scale here is nice and easy to read. H is at -8, so H is right there. I is -10 and 10. So that means I go left 10, up 10. Okay, knowing that this is a 10 by 10 grid, I just go left 10 and then up to that point. So we're left 10, up 10. That's I. And then O is on a special point. I'm going to have to erase a little bit here. O is on a special point. It's actually on the origin. So O is right in the middle. It's right there. This point is also known as the origin. Okay, that's our starting points for all of this. O, the origin. All right. When a point lies on the y-axis, what does it look like? Well, when we go back here, the point on the y-axis was G. It's 0, and then it could be just any point. So what we look at is if it's on the y-axis, it's 0, and then some y value. Okay, this is our y-intercept. This is known as a y-intercept. It's intercepting the y. Okay, same thing here. We have x and then 0. If it's on the x-axis, it moves left or right, but it doesn't go up or down at all. That's our x-intercept. Okay. All right, so moving on. So if we're looking at what's called a scatter plot and the relationships between scatter plots. So we just talked about how to actually make a scatter plot, how to put points onto a graph. Whether here we're looking at quadrant 1 or we're looking at the whole graph. So a scatter plot is a graph that shows a relationship between two variables. The points are not actually connected. Okay, so it's an independent variable, which can be any value. It's typically something like time. Time is always independent. And then a dependent variable depends on that. So as time goes on, I get older. Okay, my dependent variable is how old am I, but as time goes, I'm just getting older. Okay, a line of best fit, and that's what you see on the graph right now, models the trend or pattern. So the pattern here is going down to the right. Okay, the points start at the top and then they move down as I'm going to the right. It's going through as many points as possible, but sometimes it doesn't go through any. Okay, and that's an important thing to understand. It's really important to be able to grasp that sometimes the line of best fit doesn't go through any, as long as we have the points above and below the line are equal. So they're equal distance. So if you were to think that if I added the distance between the points on the top and the points on the bottom, they should be the same. Okay, now an outlier is a point that seems unusual. It's something that we don't typically talk about because it would be like if I put a point way up in the top right there. Okay, this would be an outlier. We're not going to consider that when we're looking at pretty much all of our data because that outlier, it would skew everything. It would make the line of best fit come up here, which that doesn't actually represent the data. That outlier is the thing that bucks the system. It's against the curve. Okay, another example here. So we have a baseball team. Recorded the number of points for each player and the number of shots they took. Okay, or excuse me, basketball, not baseball. So identify the independent and dependent variables. So the independent variable here is the number of shots they took. So that's independent. Okay, the number of shots they took doesn't matter how much they scored. How much they scored, though, actually depends on the amount of shots they took. So the independent variable is always going to go on the x values. So what we're going to do is we're going to have shots down at the bottom here. Now the most shots that we have are 67. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spots there. So I'm going to just count by tens. So what I'm going to do is I'm going to count every other square. So 20, 40, 60, 80, and be done. Okay, now on the right, or sorry, on the left, this is going to be our points. Okay, our points depend on how many shots we've taken. Now the highest here is 108. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we couldn't actually count by tens. But what I'm going to do is I'm going to count by tens because we can just extend the graph just a little bit if we have to. Okay, in this case, just to make our scale nice, I'm going to count by tens in both cases here. So we've got up to 100. Now all I have to do is actually plot my points. So player 1 shot 50 times and scored 85 points. So I'm going to go to 50. I'm going to go up to 85, and I'm going to put a point. So 85 would be halfway between 80 and 90. The next one was 32, so a little bit past 30, up to 54. So 32, 54. So kind of right there. Now, I'm trying my best to put the points exactly where they should be, but sometimes they're going to be a little off, and that's okay. Okay? We want to do our best. If we could make our scale a little more accurate or use some sort of graphing software like Desmos, that's obviously going to help us out, but it's not always possible. So we've got 24 and 36, it's kind of right there. 15 and 24 would be kind of in there. 34 and 60 would be up in here. 67 and 108. So this is kind of the guy that hogs the ball and shoots all the time, but still scores a fair bit. So 67 and 108. 19 and 34. And then last but not least, 10 and 20. So there's all of our points. I'm going to make them just a little bigger so we can see them nice and clear. Okay, there's all of our points. We've got our graph. Okay, find the line of best fit. So what I'm going to do is we're going to just estimate the line of best fit here. Okay, I can't move my line as well as you guys can. I would take a ruler or some sort of ruler device, flat edge, you might call it, and I would just do that. I'm going to try to move this down just a touch. There we go. And then I'll take the end of it and yeah, something like that. That's about the line of best fit. Okay, now your answers might vary from mine just slightly. Okay, so describe the correlation between these variables. Well, the correlation here is the more shots I take, the more points I score. The more shots, the more points. Correlation is how do they relate to one another. Well, the more points. Okay, so the more shots I take, the more points I get. If a person shot 40 times, how many points could they expect to score? Okay, so what we need to look at here is 40. And we'd go up to the graph, and we'd go over to here, and they would score about 65 points. So I would say about 65 points. Okay, now it says, is this interpolating or extrapolating? We're going to get back to this in a few minutes. If a person's shot 90 times, how many points? So if they shot 90 times, I'm going to need to extend my line to figure this out. If they shot 90 times, they're scoring probably, I don't know, I'm going to be way up here. So let's go 110, 120, probably around 140, 140 points. So about 140 points. Again, it says, is this extrapolating or interpolating? And we're going to come back to that. Next, sorry, I did that question wrong. Let's go back to that. I did that as how many shots they took, but they actually scored 90 points. So what we want to talk about there is just going over here and coming down. So it would be just shy of 60 shots. So probably, let's say, about 58 shots. Whoops. All right. A little bit more. So what is interpolating and extrapolating? Well, what interpolating is taking a point that's inside the data on the line of best fit. So using your line of best fit, so line of best fit to find something in the data. So to find something in the data. So if I was looking at this, if I used it to find like this point, that's interpolating. Now extrapolating is using it to find something outside the data. Okay, so using line of best fit, to find something outside the data. We're using a trend to anticipate an answer. Okay? Which of these is the line of best fit? Why are the other ones wrong? Well, if I look at the first one kind of looks like the line of best fit, but it's not really following the data. So that one's wrong because it's not following the data. The second one's wrong because we have way more points underneath. Same with the last one. We have way more points underneath. This one clearly is following the data, and the points are even, so this is our line of best fit. Okay. Going back to the other question, these were both interpolating because they're both inside the data. Okay, we have a data point up here, and a data point here, and a data point here, so it was always inside the data. Relationships and correlations. Okay, so is there a relationship between the dependent and independent variable? Does the y depend on the x? Okay, so what we're looking at here is a line, or is it nonlinear? Or is there no correlation? Second, is it positive? So is it going up to the right, or negative going down to the right? And finally, is it weak or strong? So if I were looking at this, I would say that the first one is linear. Okay, so it's a line. It's negative because it's going down as I move to the right. Okay, it's going down as I move to the right. And I would say it's strong because all of the points are pretty close together. Okay, the one right below it, again, it's following a linear path. Okay, you could make a line of best fit. It's positive because it's moving up to the right. But I would say this is more moderate. Okay, so it's a moderate positive linear relationship. Typically, you would read it backwards the way I'm writing these. Okay, I'm going to go up to the top right. So this one, we're going down this way. You can see a trend. Even though it's a little bit harder, we probably have an outlier here. So this is linear. It's negative. And it's probably moderate to weak. Okay. This one's a positive, linear, or positive, strong linear relationship. So there you go. I wrote that one correctly. So positive, strong, linear. And then the last two, I'm going to do the one directly below that one. This one is a very strong relationship, actually. It's non-linear. And we would just say that it's a strong non-linear relationship. Okay, because it actually is both positive and negative at two different parts. And the last one here, the dots are kind of everywhere, so this is no correlation. Okay, this has absolutely nothing going on it here that gives us a line of best fit. Another thing we need to look at is what is a hypothesis? So a hypothesis is an educated guess. Okay, it's a prediction, but it also typically has some background information about that. It's about some sort of relationship. So a hypothesis between the amount of sunlight and plant growth. So I would hypothesize that the more sun equals or is going to produce more plant growth. So it is producing more plant growth. And that's not a great sentence, but you get the idea. The opposite of that would be less sun. Okay, so less sun is producing more plant growth. Okay, it's the opposite thing. Or you could say the more sun, the less plant growth. Okay, both the same thing. Couple more slides, almost done. Okay, so state which variable is independent and dependent. Okay, so we're just looking at dependent and independent. Which one depends on the other one? Okay, so we're still on day one here, but we're just rolling right along. So day one. What is the relationship between the world's population and the time? Well, we said that time is always independent. So we know that the world's population depends on the time. Okay, world's population and time. Okay, the next one is the relationship between speed of a car and stopping distance. Well, you have to think, which one depends on the other one? Does how much I stop depend on how fast I'm going? Or does how fast I'm going depend on how much I stop? Well, if you think about it, the stopping distance really depends on how fast I'm going. If I'm going 2 kilometers an hour, I can almost stop instantaneously. If I'm going 100 kilometers an hour, it's going to take a little longer. So the speed of the car is independent and the stopping distance dependent. Is there a relationship between the amount of alcohol consumed and response time? Well, if I don't have any drinks, my response time should be good. The more drinks I have, the less quickly I'm going to respond. So response time depends on alcohol consumption. Okay, that's just a science. Those are really 3 science things. The first one's talking about population growth. The second one's talking about speed and velocity. And the third one's talking about biology. Last thing, so we're going to now interpret this scatter plot we've got here. We've got age and height. We've got 7 people sitting there. We've got Alice, Brenda, Kathy, Dennis, Earl, Frida, and Gavin. Now, Gavin is hard to see. Gavin's this little baby. There's Gavin. So we'll do that. All right. So when I'm looking at this, the first thing we have to do is match the name with the person. Okay? So age and height. So the first thing I notice is that the lowest age and the lowest height should be an easy one. That's number 7. It's the smallest age, smallest height. That's Gavin. Okay, Gavin's often missed when we're doing this, but because we're talking, it's a little easier. The next one is the next shortest person, and it's the next youngest person. So that's probably Kathy. It's got to be, because Kathy's the next shortest. So we've got Kathy. Now we're going to assume, based on the picture, that we can tell that Brenda is younger than Earl or Dennis. So Dennis is older and Brenda is younger. So O and Y. Same thing over here. I know it doesn't look, and it would be pretty hard to tell. You could argue either way. I'm going to say that Alice is older than Earl. And then it doesn't actually matter about Frida. Frida's nice and easy to see because she's the only one with a different height. So she's number 3. So there's Frida. Now we need to look at the next taller people. So we've got 4 and 5. So 4 and 5 are the next ages, but their heights are different. Okay, so if I were to look at the next thing, I'm going to look at the height, and I'm going to say I'm looking at 1 and 4 are the same height. So Brenda is younger, because 1 is younger than 4. Oh, sorry. 1 is older than 4. So that means that Dennis is older than Brenda. And finally, 2 is older than 5. So that means that Alice is number 2 and Earl is number 5. All right. Does age have a strong positive correlation with height? And I'm not going to write these out. I'm just going to talk about them. Age does have a strong positive correlation with height to a certain point. Eventually, everybody's kind of the same height. Okay, obviously people are different, but as we age, this graph would eventually do something like this if we drew a line best fit. Okay, we're not going to get any taller. We're not going to get any taller, but we are going to get older. Okay, we're getting older, but not any taller. It might actually come back this way. Okay, you kind of shrink as you get older. Do you think the variables are put on the appropriate axis? Well, I would say no, because we talked about this. The dependent variable should be on the x-axis. If we look at this, age should be down here. Height should be up here. Okay, because height depends on the age. It depends on how old we are. Would weight versus age show a strong positive correlation? I think it would be very similar. As you get older, you put on weight. Okay, that's just from growing. That's just from getting taller. Okay, it doesn't matter if you're gaining weight because you're trying to work out or something. As you age, you get bigger. Okay, until you stop growing, you're probably going to be putting on some weight. So can you think of a variable? So these are things that you would think about. Can you think of a variable that has a strong positive correlation with age? Okay, can you think of one that has a strong negative correlation with age? So strong positive correlation with age, we just talked about a bunch. You could say like head size, hair. A strong negative correlation with age. You could say hearing. You lose your hearing as you get older. Okay, so those are some things that we can look at.